Hello everybody, welcome into another lesson. So today we are going to talk about taking the inverse of a 2 by 2 matrix. In general, in order for a matrix to have an inverse, two things must be true. One, the matrix has to be a square matrix. So that means it has the same number of rows as it does columns, like a 1 by 1, a 2 by 2, a 3 by 3, a 4 by 4, so on. The highest we're going to get in this course is up to a 3 by 3, which will be its own lesson because those are more extensive. But this lesson will talk about a 2 by 2 matrix. So we can also, in another lesson, we're going to talk about how to use inverse matrices to solve systems of equations. But in this lesson and the next one, we're just going to talk about finding the inverse of a matrix in general. But anyway, I digress. So we were talking about two things have to be true for a matrix to have an inverse. One, of course, it's a square matrix, and two, the determinant's not zero. That it's not zero. If the determinant's zero, then it can't have an inverse. It's not invertible. So here you have regular matrix A, which has entries A, B, C, and D, which represent various constants. To find the inverse matrix, which is denoted as A to the negative 1, meaning A inverse, is going to be 1 divided by the determinant of A, which becomes a scale factor, times the new matrix of, you would take your D and your A and switch places with them, and then just negate the B and C positions. So A inverse is 1 over A as a scale factor, 1 over the determinant of matrix A as a scale factor times the new matrix of where D and A switch places, and then you keep B and C in the same place, you just negate B and C. The idea is then that if you take A and multiply by A inverse, you'll get the identity matrix denoted as I, capital I, which for a 2 by 2 system, the identity matrix is 1, 0, 0, 1. It's really the same idea as if you took like any number times its reciprocal. Any number times its reciprocal is equal to 1. It's kind of the same idea, only we're doing it with matrices. But it has to be A times A inverse. If you do it the other way around, you may not get that. And this is the closest we will ever get to matrix division. There really is no way to do matrix division. The closest you can come to doing that is taking a matrix and multiplying it by an inverse matrix of another one. That's as close as you'll come to matrix division itself. Now, the only matrix that is truly equal to the inverse of itself is the identity matrix. If you take the identity matrix, it's also equal to the inverse of itself. Otherwise, no other matrix is equal to its inverse. But, and also something about properties of matrices with their inverses, that if you took their determinants, you'll notice the determinant of a matrix and its inverse are reciprocals of each other. But we'll get started here with some examples, and I'll show you for the first example how to check and see if you got it right. So we have our very first matrix here, matrix A, which has entries 4, negative 5, negative 3, and then 4. Alright, so there's matrix A with entries 4, negative 5, negative 3, and 4. So, first thing you want to do when you have a matrix, before you can even try to find its inverse, is find the determinant. So, take that determinant of A. Let me denote that real quick. So, take the determinant of A, which is going to, of course, set up your determinant notation for 4 -5, -3, and 4, which will end up giving you, of course, 4 times 4 is 16, minus -5 turns into +5 times -3, that'd be -15. 16 minus 15 is 1. So the determinant of this matrix is +1. Now, we know the determinant, so we can start to find the inverse. Once you know that, you set up a to the -1, which means a inverse. You're going to take 1 and divide it by that determinant of a, which was 1. Take that times the matrix. Okay, so your A and D switch places. In this case, it's going to stay the same, the 4 and the 4. But your B of -5, you'll negate that. You'll get +5. Then that C of -3, you'll negate that. You'll get +3. Which means that A inverse, then 1 over 1 is 1. You'll just get the matrix 4, 5, 3, and 4. Whoops. That would equal your A inverse. Should be the matrix 4, 5, +3, and +4. Now, how you can check to make sure you got it right is you multiply A times A inverse, and you should get the identity matrix. If you get anything other than the identity matrix, you got it wrong. So take your matrix A, which in this case was 4, -5, -3, and 4. And then take your A inverse, which was 4, +5, +3, and 4. Alright. So, matrix multiplication, they're both the same dimensions. They'll definitely multiply and produce a matrix that has a 2 by 2 matrix. So for the top row, take your 4 times your 4, which is 16, plus you'll take that -5 times your 3, which actually turns into -15. Alright, so that's just for your first entry. And then now for your second entry in the first row, take that 4 times that 5, which is 20. And then take that -5 times that 4, which is -20. Alright, so we're done with that. Now for the first entry of the second row, take that -3 times 4, which would be -12. And then take your 4 times your 3, which would be +12. And then for the second entry of the second row, take that -3 times 5. That's going to be -15. And then take your 4 times your 4. That's going to be +16. And what do you know? You end up getting 1, 0, 0, 1, which is the identity matrix. So yes, you actually got it right then if you said your inverse matrix was 4, 5, 3, and 4. So if you multiply the original by the inverse and get the identity matrix, then you got the right answer for the inverse matrix. Okay, I got 5 more examples here. Let's figure out our next matrix. So matrix A is going to be equal to, we have the entries 6, 2, 8, and 3. Alright, so matrix A itself has entries 6, 2, 8, and 3. First thing you need to do is find the determinant of A. So you'll set up your determinant matrix. Set up your determinant of 6, 2, 8, and 3. So 6 times 3 is 18. Minus 2 times 8, that'd be minus 16. So the determinant of A would be 2. So there's your determinant of A, which is 2. Now, we can go ahead and find our inverse matrix. So to find A inverse, you'll take 1 and divide that by your determinant of 2, the determinant of A, which is 2. Now, that's your scale factor is 1/2. Take that times what you're going to do with your matrix A. The 3 and 6 will switch places because the A and D switch places. So that'll be 3 and 6. Your B and C constants stay the same. You'll just negate them. So that'll become -2 and -8 here. So now you're just going to multiply everything by 1/2. So 1/2 times 3 is 3/2. 1/2 times -2 is -1. Let's make this a little bigger, shall we? Okay, and then 1/2 times -8 is -4. 1/2 times 6 is 3. So your inverse matrix, your A inverse, would end up being 3/2, -1, -4, and 3. That's how you would find your A inverse. I have 4 more examples here. Alright, this time let's see. A is equal to the matrix of 1, 8, 1, 7. So matrix A has entries 1, 8, 1, 7. So first thing, find the determinant of A. The determinant, just set up your determinant notation for 1, 8, 1, and 7. Okay, so 1 times 7 is 7. Minus 8 times 1, that'd be -8, giving you a determinant of -1. So your determinant is -1. Now we can proceed to find A inverse. So to find A inverse, you'll take 1 and divide it by your determinant of A, which was -1, which becomes your scale factor, times you'll take your A and your D entries, the 1 and 7, you'll switch them around. So put 7 where A is, 1 where D is. 8 and 1 will stay in the same place because your B and C entries stay in the same place, but you negate them. So then you'll have -8 here and -1 here. Well, 1 divided by -1 is just -1. So now you'll just multiply everything in the matrix by a scale factor of -1, giving you -7, +8, +1, and -1. So your A inverse will end up being -7, 8, 1, and -1. Alright, I got 3 more. A, that matrix is going to be -7, -2, and then we had -4 and +1. So there's our original matrix. First, let's find the determinant of A. So that determinant is going to be, of course, -7 times 1 is -7. Minus -2 turns into +2 times -4, that'd be -8. So the determinant of A is equal to -15. Alright, so we found the determinant to be -15. Now we can start to find A inverse, which is going to be 1 divided by your determinant of A, which is -15, which becomes a scale factor, times the matrix here. Well, your A and D switch places, so 1 will go here, -7 will go here. Your B and C stay in the same spot, but you negate them, so -2 turns into +2, -4 turns into +4, So now you just multiply everything by a scale factor of -1/15, giving you the inverse matrix of -1/15, -2/15, let's see, -4/15, and then +7/15. That would be your inverse matrix of A. Would end up being -1/15, -2/15, -4/15, and +7/15. All right, I have two more, then we're done. All right. This time, let's see, A has entries of 3/2, 1/2, -2, and 1. So A has entries of 3/2, 1/2, -2, and 1. So let's start out by finding the determinant of A. So, of course, 3/2 times 1 is 3/2. Minus 1/2 times -2, that would turn into +1, which is going to give you a determinant of 5/2. So the determinant of A is 5/2. All right, now to find A inverse, you'll take 1 divided by your determinant of 5/2 times the matrix where you switch your A and D around. So 1 would go here, 3/2 are going to go here, and then your B and C stay in the same place, but you just negate them. So this will become -1/2, and then this will become +2. Alright, so 1/5 is actually 2/5. So this will actually end up being 2/5 as a scale factor times the matrix of 1, -1/2, 2, and 3/2. Now we do our scalar multiplication, we'll get what A inverse is truly equal to. So 2/5 times 1, of course, that's going to give you 2/5. 2/5 times -1/2 would actually give you -1/5. All right, 2/5 times 2 would give you 4/5. 2/5 times 3/2 would give you 3/5. So the inverse matrix of A would be 2/5, -1/5, 4/5, and 3/5. And I got just one more for this lesson, then we're done with the lesson. Inverse of a 2x2 matrix really isn't that bad. What is the last one of the lesson? A has entries of 4/5, 3/4, alright, then it also has -1 and then 5/2. So yeah, that's a nasty looking one because of the fractions. But let's start out with finding the determinant of A first. The determinant, of course, okay, 4/5 times 5/2. Why don't we just do this here? 4/5 times 5/2 minus that 3/4 times the -1. So this will turn into, see, 5's cancel out, 2's gone, this becomes a 2. This will simply turn into 2 plus 3/4 which would end up giving you 11/4. So the determinant of A is equal to 11/4. Now, to find the A inverse, you're going to take 1 and divide it by your determinant of A, which is 11/4, times this matrix. So A and D swap places, so you would put 5/2 here, put your 4/5 over here, and then B and C stay in the same spot, but you negate them. So this would become -3/4, and then negate the -1, that becomes +1. Well, 1 over 11/4 is going to turn into 4/11 as your scale factor, and then just multiply it by this matrix of 5/2, -3/4, and then 1, and then 4/5. Alright, so 4/11 times 5/2, that would end up being 10/11. So A inverse, first entry in that, would end up being 10/11. Alright, 4/11 times -3/4 would end up being -3/11. 4/11 times 1 is just 4/11. And then 4/11 times 4/5, that's going to be 16/55. So the inverse of A is the matrix with entries 10/11, -3/11, 4/11, and 16/55. So that's really it for finding the inverse of a 2x2 matrix. Next lesson we'll talk about the inverse of a 3x3 matrix. So I hope everyone has a great day. Take care.